Now we are ready for the confusing part. While studying wind tunnel data, I found that it's more efficient to fly fast. So Reynolds number is proportional to the speed, so at higher Reynolds number, so for instance here, you have minimum drag. The same is for this graph and for many other graphs. But if you fly slow, you have to have a lower Reynolds number, then you have significant drag. It's kind of, you think it should be the opposite. So the faster you fly, the more drag you have. But according to those graphs from the wind tunnel data, it's not true. So I decided to plot some graph using XFoil and to see what's going on. So I have plotted those graphs. To do that, I have been using this beautiful software, XFoil R5 software, and it's beautiful because you can do many things. For instance, you can run the batch analysis, you can define the number of Reynolds number that you wish, and then you can run simulation. And as the result, you will get all those graphs, and then you can just export all those graphs to the text file. And after that, you can use Python to analyze the data. So I have been using Python. Python is more convenient for me. As a result, I have obtained those beautiful graphs. So what on those graphs we have the lift coefficient versus alpha, we have the drag coefficient versus alpha, then we have something that you cannot get from the wind tunnel data. We have the drag, pressure drag, basically the drag which is caused by the lift, I would say, just the way the foil redistribute creates the forces, and you have projection of this force on the direction of the airplane, so you have the drag, pressure drag. You also have the viscous drag, basically the molecules rubbing around the surface of the airplane, and some vortices are created and so on. And then you can also have the graph where you have drag versus where you have drag coefficient versus lift coefficient. So the first thing that you should note that we have the same picture as from the wind tunnel data. So if you fly slow, let's say 10 meters per second, you have huge drag. If you fly fast, 80 meters per second, you have the minimum drag. The same kind of picture for the pressure drag and for the viscous drag. For whatever reason, you have to go very fast to have the minimum drag coefficients. I decided to look into the wing design as I have done previously, in the previous video. So I have plotted the same graphs for the wings, and the picture is the same. So you have to go very fast to have the minimum drag. The same is for the inviscous and viscous drag. The only small difference is that for the wing, actually for the inviscous drag of the wing, you have the zero drag for the slow speed, so wind kind of does not like to move. But the total drag still the same picture, so the faster you go, the smaller is the total drag. What you can do also, you can plot the wing and the foil graphs on the same picture, and you see the difference between the wing and the foil, how the wing is actually going to affect the drag. And what else? So I was kind of still confused. I got the same result as I've seen in the wind tunnel data, and I was thinking maybe it's because I haven't looked at the wide range of operation. So I decided to basically to plot those graphs for the very wide range. So basically speed goes from 10 meters per second to up to almost the speed of the sound. So I have plotted those graphs, again using the beautiful software, this software, and the results are the same. Kind of the drag likes to have the minimum drag. You would like to fly fast. So there is no kind of strange behavior somewhere else. Still have to go very fast to have the minimum drag. The same for the lift versus drag coefficients and so on. What next? I decided to plot those graphs just to make sure that I got it right. So I took the data and I basically plotted the slice. So for instance, here I have the lift coefficient versus speed. So we have speed from 0, no, not 0, but 10 meters per second to 250 meters per second, and we have the lift, how it behaves if you change the speed of the airplane. So we see at angle of attack alpha equivalent to 1. We see that C alpha grows till it reaches approximately 40 meters per second, and then it drops. And drag behaves again the same as we expected, as we have seen previously. So the faster we go, the smaller the drag. So the total drag, the viscous part of the drag, and the pressure drag. Alpha equivalent to 2 degrees. Similar picture. Again, drags like to have the minimum drag, we have to fly fast, and alpha equivalent to 3, the same picture. Lift coefficient behaves a bit differently at alpha equivalent to 3, but picture is the same. And we have resolved this puzzle actually very easily. You can resolve this puzzle very easily if you look at those equations. So those equations. So lift and drag force are proportional to the square of the speed. So what lift coefficient and drag coefficient do, it's not very important. If you're concerned about the plane design, you would have to consider the lift and drag force. And those forces are proportional to the square of the speed of the plane. So I have plotted those graphs here. Okay, so this is the force drag force versus speed. And then you see that the drag force is increasing as if you increase the speed of the plane. So it goes like this. And for all angles of attack, you have increasing drag force. So this is the source of my confusion, and I haven't seen anywhere that this subject was discussed in details. Well, but I haven't read many books. But anyways, so now we're ready for the design. We know what is the lift and drag coefficient. You know, those coefficients are unitless. We know how to get those coefficients from the wind tunnel data or from the simulation. And we know how to get the forces, lift and drag forces. So we can continue. There were also small confusion in the previous video where we will run simulation of wings of different aspect ratio. And for this purpose, we were using XFoil R5 software. Just to remind, Audience aspect ratio is the ratio between the wingspan and the average chord length. So this is the aspect ratio. And in this software, we can extract few parameters from the files after the simulation. And those files include few types of drag. So the first drag is the total drag. The total drag is equivalent to induced drag and viscous drag. And the way the software is running is computing the induced drag, which is totally dependent on the wing aspect ratio, on the wing size. So basically, when we have a 3D dimensional object, not a 2D foil, so by this kind of transition, we have induced a drag happening. So it's not viscous or inviscid drag, and the second is viscous drag. So the viscous drag is actually the drag which was obtained from the XFoil software. It's part of the XFoil R5 software, but this is XFoil way to get the viscous drag. So on those on this graph we can see first what we can see is inviscous drag. So this is drag related to the wing. It's in blue line. So this is the blue line, and we know that at zero angle of attack we have zero in inviscid drag. So the second line is viscous drag. So this is the drag from the XFoil, the green line, and if we sum those two up, so we get the total drag. So the total drag, as you can see, the value of total drag extracted from the file is the same as the value of inviscid drag plus viscous drag. Okay. Second observation is just the refreshment of the previous video. The second thing is that this inviscid drag, depending on the wing aspect ratio, behaves in interesting way. So when we have the angle of attack 0, we have no inviscid drag. So we look here, there is no drag. And on this wing we have the aspect ratio 0.5 degrees, and then we have small vortices are forming. If we increase the angle of attack to 3 degrees, we have more vortices and high drag, and in this case, for instance, we have angle of attack equivalent to 8, and then we have huge vortices are forming on the back of the wing, and that's what we can see. So we increase the alpha and we see how this curve is bending up. So we have more drag, and this drag is basically the main drag for the plane with a three-dimensional wing, whereas viscous drag is kind of becomes smaller than inviscid drag because of the limit of the aspect ratio. Okay, and now let's go to the results from the previous video we have obtained, and the right thing to do is to plot different types of drag: total drag, induced drag, and viscous drag over the CL coefficient. So we have the lift coefficient on the x-axis, and we have the different types of drag over the y-axis. So we run the simulation for wings with different aspect ratio. So the longest wing was 20, so it's the wingspan was 20 times as long as the wing chord. Then we have 10, 5, and 2.5. So if you plot this against the C lift coefficient, it all looks fine. So we know that the lowest drag is for the longest wing. So if we look at the lift coefficient, for instance, the given lift coefficient, and we can obtain this lift coefficient using different wings. But we're going to have different drag. So the highest drag is for the wing with aspect ratio 2.5, and then we have a bit smaller drag, and the minimum drag is for the wing of aspect ratio 20. So this is totally expected. So the long wing definitely wins this competition. Then we look at the induced drag. So the induced drag is again expected. So we have the smallest induced drag for the long wing, and we have the highest induced drag for the short wing. And then something interesting, so we look at the viscous drag. So once again, the viscous drag was obtained from the XFoil software, because you cannot get this drag using the simulation methods. So those methods are kind of classical method, and were derived from not viscous inviscid assumption. So you cannot get something from this way of computation. So we obtained this viscous drag from the XFoil simulation, and now we can look at those curves. So for all aspect ratio we have the same kind of curves. So you might think, why is that? And the answer is pretty simple, because XFoil does not include the aspect ratio in consideration. So it computes the results for the 2D foil, and of course you're going to have the same results for various aspect ratios. So it's not part of the simulation, not part of the picture. So the same graphs are obtained. So this is the right way to do. And if we plot the drag versus alpha coefficient, then you might find something strange happening. You might see that, for instance, a small aspect ratio, you have a smaller drag than for high aspect ratio wings. And this is this is correct. Yes, this is correct for the alpha. So you might have some alphas at which you're going to have a smaller drag for shorter wing. But again, we don't care about the alpha. What we care is about C lift, lift coefficient, and the efficiency of the wing, which is basically the ratio between lift coefficient and drag coefficient. So this is kind of not needed, and it's kind of strange and a very peculiar result. Okay, and so we have plotted this graph for the speed of 20 meters per second. Now we go to this graph, and now we have speed 80 meters per second. The picture is totally identical in a sense. The only difference is that, again, with higher speed we have smaller drag. Drag is dropping, as we have seen in the first part. So we have less drag, 0.3, and here we have 0.45. So the drag is smaller, but it behaves totally the same way. So the wing with the high aspect ratio is winning the competition, have the smallest drag. The same is for the viscous drag, induced drag, kind of again. That's expected. And then we have graph for the viscous drag. Again, the same single line, because we got the result from the XFoil. But to get the total drag, we should sum up this curve with the induced drag curves, and then we have the total drag curves are like that. Okay. Now we are ready for the conclusions. And the first observation is that if you fly fast, the lift coefficient is close to 0. And that means that the induced drag is actually 0. So we have 0 induced drag for the small lift coefficient. So it does not matter what kind of aspect ratio we have. We can have long wing or short wing, it's not important. We have 0 induced drag, so you can have any wing. And the total drag is determined totally by the viscous drag. And for the viscous drag, we got the results from the XFoil, and the simulation is done in 2D, and the aspect ratio is not part of the picture for this simulation. So in that case, again, we have no 0 value, but this value is the same for different aspect ratios. So basically the conclusion is that it's not important what kind of aspect ratio you have if you fly high. So this is a bit unphysical. What I'm thinking that probably the viscous drag should be higher for the long aspect, for the high aspect ratio wings. So the longer the wing is, the more kind of molecules arrive around the surface and so on. So you have to have the higher viscous drag. So maybe it should be preferable to have shorter wings at high speed. But it does not follow from simulation. From the simulation we see that viscous drag is not dependent on the aspect ratio for the high speed, or for any speed. So the viscous drag is not dependent on the aspect ratio, so you can have any speed. And the induced drag is 0 at high speed. So, but if you fly slow, then you have to look at the high lift coefficient, and in that case we do see a big difference. So for the slow flying airplanes, you would like to have wings with high aspect ratio. So the longer the wing is, the more efficient this wing is, the smaller the induced drag is. But the viscous drag is also the same, it's not dependent on the wing aspect ratio. Okay, so the conclusions are as follows. So the high aspect ratio wing always wins, because the viscous drag is not the part of the picture, and the viscous drag not part of the picture because we're using those methods, and those methods are derived without viscous assumption. So those are not viscous or inviscid methods. Okay, and what else? So we can say that this software, XFoil, I think it's doing a good job. So we can see how the induced drag is different for different aspect ratio. We can see the vortices, and we can run the simulation. We can obtain some results. And I think probably if we introduce the dependency of the viscous drag on the wing aspect ratio, it's probably not going to change picture a lot. So maybe you would like to have a shorter wings at the high speed. It's hard to say, but it is what it is, and I think that we are ready for the next step.